Hello, my name is Jessica McRoskey. I'm an engineer on the research and development team at Meisner Filtration Products, who's an industry leader in single-use and filtration solutions. Today I'll be talking to you about our Separapore hollow fiber filter line and its performance during cell culture perfusion applications. Hollow fiber membranes enable tangential flow filtration, where the feed stream flows parallel along the membrane rather than perpendicularly into the membrane. The parallel feed stream sweeps through the fiber, reducing membrane fouling and prolonging filtration performance. Though flat sheet membrane cassettes can also be used for tangential flow filtration, hollow fiber filters are typically preferred for feed streams with high particulate and solids loading, such as cell debris, cell suspension, or colloids. Separapore microporous membranes are offered with 0.1, 0.2, and 0.45 micron retention ratings, and are ideal for all stages of process scalability, with effective filtration areas from 0.01 to 8.3 square meters. Our hollow fiber membranes are made from polysulfone and are manufactured with tight wall thickness tolerances and highly symmetric porosity, as you can see in these SEM images. These characteristics ensure consistent crossflow, high throughput, and long filtration lifespan. We recognize that consistency is one of the major challenges associated with integrating tangential flow filtration into your process. And correcting filter variability could require changing other process parameters to maintain batch-to-batch performance. This is why it is so important to have consistent filtration for your application. Again, inconsistent filtration will require having to change other process parameters to maintain the same process performance. By having a supply of filters with consistent performance directly increases the consistency of your process. To address this, Separapore membranes are engineered for enhanced process consistency, and that starts with the membrane morphology. Bubble point is a commonly used characteristic for porosity or retention rating of a filter. Here we can see the published bubble point values of 3 separate suppliers. I think it would be surprising to most people that the bubble point values ranges could differ so much from supplier to supplier. Although all of these membranes pass industry standard bacterial and mycoplasma retentive tests, their characteristics and membrane morphology result in performance differences across suppliers. Looking at this graph, supplier A has comparatively wide bubble point ranges for each porosity rating, which implies a broad range of filtration performance for a given porosity. In application, this would make reproducibility in your process a challenge. In addition, as bubble point values increase, flux decreases. So for an application that requires a 0.1 micron porosity membrane, you would expect to see the lowest flux and least efficiency from supplier A. Now looking at supplier B, you can see that there's a significant overlap across bubble points for different porosities, particularly with the 0.45 micron. If you are ordering 0.45 micron filters, you don't want to be wondering if one will perform as a 0.65 micron membrane, while another will perform as a 0.2 micron membrane. These unclear boundaries are a disadvantage to selecting a reliable filter for your process. Separapore has distinct bubble point separation between porosities and narrow ranges to improve your batch-to-batch performance. Due to the reliability and robustness, Separapore microfiltration hollow fiber membranes are ideal for cell culture perfusion applications. Here you can see an example of a typical tangential flow filtration loop for cell culture perfusion. Cells are suspended in solution and are pumped through the Separapore filter. The filter retains cells in the retentate, flowing back into the bioreactor. The product containing permeate passes through the Separapore hollow fiber membrane and is collected as cell-free harvest. As that permeate is filtered out and collected, fresh culture media is pumped in to maintain a consistent vessel volume and to provide fresh nutrients for cell growth and viability. With perfusion runs often lasting weeks, long-term consistency and minimizing areas of variability are key. The main way to evaluate membrane performance during a perfusion run is by recording the feed and transmembrane pressures, shown here as P1 and TMP. TMP is the pressure necessary to push solution through a membrane. So membrane fouling decreases the cross flow through the membrane, so a greater transmembrane pressure is required to maintain the same permeate flow rate. Therefore, large increases in pressure are an indication of fouling and decreased membrane performance. In this benchtop experiment, a 21-day CHO cell culture perfusion run was evaluated. The cells were inoculated and perfusion started on day 3. Throughout the 18 days of perfusion, the feed pressure only increased by 1.2 psi and the transmembrane pressure only increased by 1.5 psi. During the benchtop run, cell viability was maintained above 90% and a cell density of 54 million cells per milliliter were achieved. Overall, the membrane performance was consistent and minimal fouling was observed throughout the long perfusion run. Looking towards the future, we are continuing to expand our Seprapore hollow fiber portfolio, and we will be coming soon with an update on ultrafiltration porosity ratings. So be sure to keep an eye out for that. For more information about our Seprapore filters, you can visit our website at www.meisner.com/Seprapore. Thank you for listening to our discussion about our Seprapore filters in perfusion applications. Now I'd like to introduce my colleague Tristan Winneker, who will be covering advances in automated filling technology. Thank you.
Thank you, Jessica. My name is Tristan Winneker, and I'm a product manager here at Meisner Filtration Products. And today it's my privilege to share with you advances that we've made in aseptic filling over the past few years. These advances can provide increased filling speed and also substantial financial benefits when adopting the AccuFill aseptic filling system for your bulk liquid filling applications. For a quick overview of the presentation today, we'll be talking about the current bulk liquid filling paradigms in our industry, and then we'll take a look at an overview of the AccuFill system, and then we'll look at an analysis of the AccuFill financial advantages that can be gained. And finally, we'll look at some additional advantages and ongoing improvements that we're making to the AccuFill system. To ensure that we're all on the same page, when we talk about bulk liquid filling, we're referring to batching large volumes of liquid solutions, such as cell culture media or buffer solutions, and then dispensing that large volume of liquid into many smaller containers, such as biocontainer bags. Manifold assemblies are the most commonly deployed bulk liquid filling strategy, but they have several disadvantages, such as difficulty manipulating larger configurations and the potential for leaks and contamination at each of the connection points in the assembly. Manifolds are also time-consuming and very labor-intensive to lay out, make all the connections, fill each bag individually on a scale, and then seal each and every fill line. So now that we've taken a brief look at the most common method of bulk liquid filling, let's take a look at an overview of the AccuFill system. At the core of the AccuFill technology is an innovative single-use fill line that interfaces with a Coriolis flow meter, providing extremely accurate fills in a fully single-use flow path. The filler has 2 Coriolis flow meters, one for each fill station. The aseptic filler is controlled by a recipe-driven touchscreen HMI, which is very intuitive to use. The filler features an ISO Class 5 filling chamber, which is a self-contained, HEPA-filtered environment with continuous particulate and pressurization monitoring. All of the critical steps of filling a biocontainer, including sealing the container, are performed automatically by the robotics within the filling chamber. The AccuFill features 2 independently operated filling stations, and carts are available to support end-ported biocontainers during the filling operations. Now let's take a closer look at the financial benefits of using the AccuFill system for bulk liquid filling. In our analysis, we'll compare a 10-bag manifold assembly versus AccuFill biocontainers, taking into account the setup time, sealing time, and cleanup time, and the cost for each consumable. We'll also consider the cost and installation time of the single-use fill liner assembly. And in the analysis, we'll look at 1 liter, 5 liter, 10 liter, and 20 liter fill volumes. For our filling operations, we are assuming that the flow rates for each system are equivalent: 32 liters per minute for the manifold system and 32 liters per minute overall for the AccuFill, which equates to 16 liters per minute for each of the 2 fill stations. We're assuming a 10,000 liter batch volume and performing filling operations around the clock, 24/7, which is how some of our customers operate. We're also assuming 2 staff are required for manifold filling, for GMP verification, and for the amount of physical manipulation that's required during operations with manifolds. We're assuming 1.1 staff for the AccuFill, because while one person can operate the entire system independently, a second person is required occasionally to support operations by transporting away filled biocontainers, replenishing the stock of biocontainers to be filled, emptying the cap hopper, and other support tasks. With these staffing requirements, we're assuming a labor overhead of $60 per hour, and again, round-the-clock operation to complete the filling process. Now let's take a look at the output of our scenarios. For 1 liter fills, the total cost per batch using the AccuFill system is about $470,000, whereas for the manifolds, it's closer to $800,000. The number of 10,000 liter batches that can be completed in a year is 185 batches for the AccuFill versus only 7 using a manifold system. The output in liters per year is about 1.8 million liters filled with the AccuFill system versus about 70,000 liters filled with a manifold system. And that's a difference of just about 1.8 million liters per year when using the AccuFill. The total cost of the maximum output for the AccuFill is about $87 million, and for the manifold, it's about $5.5 million. But for the manifold assembly to match the output of the AccuFill system, the total cost would be $145 million. So the opportunity cost of not using the AccuFill is about $140 million. If you do use the AccuFill to fill these containers, the total cost savings of the AccuFill versus the manifold is $59 million. So if we take that $59 million saved in a year, divided by 365 days per year, the daily cost savings is $161,000 per day. And when considering the price of the AccuFill system, the break-even time is only 5 days. The time that it would take the manifold to match the output of the AccuFill is close to 27 years. So in 1 year, you're saving $59 million and completing 27 times more fills than with a manifold system. Looking across at the 5 liter, 10 liter, and 20 liter fill volumes, for 5 liter fills, the total cost savings of using the AccuFill system is about $36 million, and you complete the fills almost 18 times faster than you would with a manifold system. For 10 liter fills, the savings are about $20 million per year, and you're completing your fills about 13 times faster. With the 20 liter fills, the savings are almost $15 million per year, and you're completing the fills almost 9 times faster. While the AccuFill is designed for high throughput of smaller volume fills, it's also advantageous when used for larger fills of 200 liter, 500 liter, and 1,000 liter, where your total cost savings per year using the AccuFill is between $2 million and $6 million per year, and you're also filling about 2.5 times more containers with the AccuFill than you are when using a manifold system. Let's take a look at some of the other advantages of the AccuFill that might not be so obvious. First is risk mitigation. Filling containers in an ISO 5 controlled filling chamber, as opposed to the room environment, minimizes the risk of contamination. And because the fill nozzle fills one container at a time, if there's any issue with that container, only that single container needs to be removed, rather than putting an entire manifold assembly at risk. The AccuFill is also very easy to operate. Operators no longer need to make aseptic connections for every bag filled. They don't need to monitor scale weight for each fill. There's no external sealer to manipulate and store. And there's no excess tubing manifolds to set up and clean up after filling. The system is also very accurate. The Coriolis flow meters and adaptive filling capability achieves an accuracy of about 50 milliliters on any fill volume, and the AccuFill system stops automatically when the target fill volume is reached. The system also creates a digital batch record, which eliminates documentation errors. And it's also very flexible, with each fill head being operated completely independently for maximum filling flexibility and efficiency. As much as our customers love the high throughput efficiency of the AccuFill system, we're working on several improvements for the next generation of AccuFill fillers. The first is integration with a single-use pump head, which will make the entire flow path fully single-use. We're also working to improve the accuracy of our small volume fills of less than 1 liter, so that our customers have even greater flexibility in filling smaller volumes. Finally, we're creating a designated place for settling plates for environmental monitoring within the filling chamber. We're designing specific holders to accommodate the plates to meet our customers' needs for environmental monitoring during their aseptic filling. I'd like to take a moment to address a couple of commonly asked questions that I've received about the AccuFill system. Some of our customers use pressurized vessels for their bulk liquid filling applications. A pressurized vessel can be used without a pump, and the pressure required for that vessel to feed the liquid to the AccuFill system is 28 psi. Another question that I'm commonly asked is the AccuFill mobile? And it is. The AccuFill is on wheels and can be moved to any location that's convenient within your facility, and the HEPA filter can be removed from the top of the system to more easily fit through doorways. With that, it's been my pleasure to introduce you to the AccuFill aseptic filling system, and I'd like to thank you for your attention. For more information, please visit our website at meisner.com.